back in like unit 3, I sometimes ask you about f to f prime. And so maybe if f was like a cubed function, x cubed, then we talked about how the degree goes down 1, and so f prime would be a parabola, x squared. And then we didn't do this, but we might have been able to say then the second derivative would take the degree down 1 more and be x. Or I'd give you f prime and have to go back to f1 or something like that. We're going to extend this a little bit. Maybe I don't know it's a polynomial. Maybe I just know it's a function. And they give us one of these 3 graphs. How can we figure out things about the other 2? So let's go back to page 9. And we're going to look at the top here. A graph of f prime is given. So here it's a little hard to see. This is not f. This is very different from these. So I gave you f. Yeah, you could directly go from here to this one. I'm giving you f prime though. So this is different. Fill out the answers A to D based on the graph. Okay. First one, in A, find the intervals f is increasing and decreasing. So f. Graph is f prime. I'm going to go for each of A and B, parts A and B. I'm going to go back to the definition. So as a review here, I'm going to go back a page or 2. I went back to, let's see, here it is. This is like 2 pages back. The definition of increasing. F is increasing when f prime is greater than 0. It was the one where I showed you down here. Just as long as the slopes are the slopes continually positive, then it's increasing. So it's increasing on an interval if f prime is greater than 0. F is decreasing if f prime is less than 0. Slopes are negative. So increasing f prime greater than 0, decreasing f prime less than 0. This is f prime. That graph is f prime. So I just need for increasing, increasing, where f prime, this graph, is greater than 0. Greater than a y value of 0. That's it right there. So on the interval, by the way, these are supposed to match up. It's a little bit off. -1, and this is supposed to go down to 3. So sorry about that. We'll just assume it goes to that. So it is increasing on the interval 2 to 3. That's right. I mean, first you might say, wait, that doesn't make sense. Isn't it increasing here to here, right? Which is that's if it was f. Yeah, f is increasing. If this graph, if I change it to f, it'd be increasing, decreasing, increasing. But this is f prime. Oh, okay. This is f prime. So the definition of f to be increasing is where f prime is greater than 0, 2 to 3. It's decreasing where f prime is less than 0, but below the y value of 0. So it's all of this. Now I'm going to separate it not at 0 there, because it's 0 at an x value of 0. So it's decreasing from -1 to 0, union 0 to 2. So again, f prime is below the x-axis. So on this type, you're looking for, just looking at the axis, x-axis above and below. Let me do part B. A and B kind of go together, C and D as well. So let me do part B and then see what questions I can answer. Find the intervals f. This time is concave up and concave down. So maybe you can go back, I think, a page. Nope, 2 pages, sir. Concave up and concave down. I'm going to use this. There's kind of 2 definitions. Concave up is when f prime is increasing. Concave down is when f prime is decreasing. I'll write that on our page. Concave up, f prime increasing. Concave down, f prime decreasing. time, I'm answering concave up to start. The interval, it is concave up. F is concave up. It is when f prime is increasing. Well, this is f prime, this graph. I just need to see where f prime is literally increasing, going up. So it's increasing from there to there. Decreasing, and then it's supposed to be about 1. It's increasing all the way up there. All right, that's f prime. That's where f prime is going up. So it's concave up on those intervals. So -1 to 0. Union 1, 3. It'll be concave down when f prime is decreasing. That's f prime. It's decreasing, going down 0 to 1. What I'm going to do in a minute is you'll see this. I'm going to draw a graph of what this function f could look like based on all this information. So A, f prime increasing and decreasing. That's where f prime, just looking above or below the axis, x-axis. Concave up, where f prime is literally increasing, going up, and down for concave down. I'm going to answer on A or B. Anything to clarify there? Okay, so the key thing here is this is f prime, not f, very different. Okay, I'm going to use parts A and B to help me get C and D. Part C, find the x coordinates of all inflection points. If you remember, inflection points occur when the concavity changes. So when the concavity switches positive to negative or negative to positive. So let's just look at part B. -1 to 0 is concave up. But then at 0, it switched. It became 0 to 1, concave down. So at x equals 0, it switched from concave up to concave down. It's concave down 0 to 1. Then from 1 to 3, it's concave up. So it switched at 1. So this is directly going to put from part B. So we got that. That switched. So I can just look at part B, and that will tell me that. Part D, find x coordinates of all local extrema. This is first derivative test. First derivative test. Let me go back to that one. That one just says, go back here. This is the one that says this, if it changes. I had a picture of this. Oh, here. Oh, I know. I'm at the wrong spot. It's down here. It's this one. If it changes from positive to negative, like here, then it's a local max. And if it changes from negative to positive, it's a local min. And so I can just look at part A. Because this is when f prime was positive and f prime was negative. So let's see. Starting off right, -1 to 0, it was f prime was negative. Then 0 to 2, it's still negative. So there's no change there. But then from 2 to 3, it was positive. And so it did change at 2. So I'll just say I'm going to answer from part. I used part A and really the first derivative test. From all this, I'm going to sketch a little graph of this in part E. So any thoughts on C or D? Okay. Now, I'm going to make a grid very similar to this one. Kind of go like this, give myself space like that. Try to match it up here, but pretty similar. -1, 0, 1, 2, and 3. That's not going to be perfect, just similar grid as before. This is a possible graph. All right, we don't have every information we could ever know about this, so it's just some information. They do give us, though, f of 1 is 0. That means that x equals 1, y is 0. All right, so I'm graphing f. This is the original function. They provided us the graph of the derivative function. We're working backwards. We're getting the original. I'm using the information from above, mainly parts A and B. Okay, so here we go. I'm looking at each basically interval, -1 to 0, 0 to 1, 1 to really 3. Okay, so let's see, -1 to 0. It is decreasing and concave up. Alright, if you'd like, you could even decreasing, concave up. Okay, concave up shaped like a cup. You can't have it go back up like that, so it's just going to be more like this. So it's decreasing. So I'll start somewhere here. It doesn't really matter where I start. It's decreasing, but concave up. Right, that was from -1 to 0. Now I'm going to look at 0 to 1. It's kind of my next interval I need to look at. So let's see, 0 to 1. It's still decreasing. That's included here from the 0 to 2. So it's decreasing, but now it's going to be concave down. So this one, right. So it's decreasing and concave down. So it's going to be shaped like a frown. I'm going to pick it up right here. Still going to decrease. Now it's going to, it's the best I can do to go, so it goes through 1 there. So you can see right here it did turn, and now it's shaped like a frown and decreasing. Next thing I need to do is 1 to 2, but I think we're just going to overlap 1 to 3 pretty much. No. I'll do 1 to 2. Yeah. So 1 to 2 is decreasing. Part of this one. It's decreasing. And now we're over here in this part 1, 2. It's concave up. So it's decreasing, but it's going to be shaped like a cup now. I started to increase it. Let me try that again. So it had to decrease from 1 to 2. And be shaped like a cup, not a full cup, but just the left side of it. And now I'll finish off 2 to 3. So I'm actually, for the first time I'm here, it's increasing. So it's increasing from 2 to 3, and on part of this still, it's concave up. So it'll be shaped like a cup. So now I'll be increasing and shaped like a cup. Again, this is just an estimate, but it gives the overall shape of the graph, which is nice. So let's verify everything. We'll look at A. It's got to be decreasing everywhere except 2 to 3. There's a break here, it's even. And decreasing, and then 2 to 3, it's increasing. Then let's concavity. Again, this is where we kind of see concavity really at work. This is how it's turning. So concave up, shaped like a cup to start. Yeah. Then from 0 to 1, concave down, shaped like a frown. Then the rest of the way, 1 to 3, shaped like a cup. So, all of those really coming into play. And we have, you can see there was a point of inflection where the concavity changed there and at 1. The other one here is there's a local min here because it was decreasing and then increasing. Sounds good. I'm going to do an example to finish up about just relating this back to velocity and acceleration. Any thoughts on this one, though? This can be a little abstract, going from f prime, nothing back. But it's all based on these definitions of increasing, decreasing, and concavity. Thoughts? Well, let's finish up the one at the bottom. Back to our best friend from Unit 3, was it, or 4? Particle motion. Right? I love this. Right, there's axis, it's going back and forth. But to illustrate it, we curve it like this. Here's a position function. Time starting at 0, moving forward. It's a particle. Find the velocity acceleration. Basically describe the motion of the particle by finding out what the velocity acceleration are doing. Let us first get the velocity. How do we get that? First term, so remember position, then velocity. Nice. So I do the derivative of position. 6t squared minus a good power rule. Minus 28t plus 22. And I need to finish that in a minute, but let me go ahead and just get the acceleration. Acceleration is then what? How do I find it? There's position, derivative gets you velocity. Then what?
Speed equal to average rate of time.
You think an average velocity is? Derivative of velocity gets you the acceleration. You should continue as the position, velocity, acceleration. If you said it. So 12t minus 28. I kind of put these side by side because we're going to be doing the same thing for each one. It's just one's velocity, one's acceleration. Okay, so we got to find what's happening with the velocity. So what I'm doing is exactly what you do here with first derivative for increase, decrease, second derivative for concavity. I'm doing that here. So what's going on with the velocity? Set it equal to 0 to find the key critical points and solve. What's going on with the acceleration? Same thing. Okay, so let's solve the first one. Quadratic formula would work right off the bat. One. I can factor out a 2 at least, though. Yeah. So we got the 3t squared minus 14t plus 11. That's the most GCF I can do. Okay, and then factoring by a trinomial will work. So, split in the middle, guess and check, slide divide, whatever method you use will work. I'm just going to do mine up here. I'm going to do guess and check. Our first terms in the binomials will be, I have to multiply to get 3. I'm going to choose 3 and 1. So 3t and t. Because when I FOIL, those would be 3t squared. The second terms in the binomial, I have to multiply to get 11. So it has to be 1 and 11. Now I'm going to put the 1, let's see, I need to be 14 in the middle. So I'm going to put the 1 here so it multiplies to get 1t, and 11 here. Nope, I messed it up. 11 here, so it multiplies to get 11t, and 1 here. So it's 3t. If you prefer your other method, that's fine. I'm just showing you what I would do. They got to multiply to be positive, so both of these need to be negative in order for it to be a negative 14t.
3t minus 11. T minus.
Mm-hmm. So I do a guess and check type thing. 3t times t is 3t squared. Outside is negative 3t. Inside is negative 11t. That's negative 14t. And then the last is negative 11, negative 1 is positive 11. All other methods should work too. Okay, this one gives me no solution. 2 equals 0. This one will give me 11 thirds. This one will give me 1. And so I describe the velocity. I put these on a number line. 11 thirds is 3 2 thirds. So I'll put that to the right. So 1, 11 thirds. I plug in the values. Let's see, 0 will be unlocked to 1. Oh, wait. Did this start? This probably started at 0. I guess I can include 0. It says we can include 0, so that's fine. Let's go 2 here, and then 3 and 2 thirds. This would be 4 here. 11 thirds is 3 2 thirds. Now, I'm finding things out about the velocity, so naturally I'm going to plug these into the velocity. Plug them in up here. Let's do a few. If I plug in 0, this will be 0, 0, 0, 0, positive 22. If I plug in 2, it would be 2 squared, which is 4, times 6 is 24. Minus 28 times 2, which is 56, plus 22. It's going to be 46 minus, it's going to be negative 10. Let's go ahead and get the last one. I'm just going to give it to us as positive. I get rid of my test values, and now I can talk about what's going on with velocity. Velocity is positive because it's increasing when. Let's see, we start at 0. So I'm looking here. So I can't go negative here because it's 0 to 1. Union, and then I pick up at 11 thirds. 11 thirds to infinity. And I can say the velocity is negative between 1 and 11 thirds. Okay. Hopefully you can see, this is good to do. It's a great, actually perfect timing for a review, but it's really just what we do with f prime. First derivative, z equals 0. These are really like the critical points. Then these intervals are where that f prime will be increasing and decreasing. We can actually get a local max or min as well. It's really just the same as f, doing what we do for f prime. Let's finish up with the same thing for acceleration. We set it equal to 0 and we'll solve. It's a really easier one to solve. I'm just going to add 28 to both sides and then divide. You could also have done a GCF and then. So let's divide by 12. So I get 28 twelfths. So I can divide by 4, right? So it's 7 and 3. So 7 thirds. So this is like the key value where the acceleration is most likely going to change. But to see that, we'll make a number line. And since we're working in acceleration, I'll try some test values on the left and right of 7 thirds and plug them in. I got 0 or 1. Let's see, 7 thirds is 2 1/3. Let's do 3. So I plug in 0. Here's my acceleration, 12t minus 28. Or use this one. Plug in 0. I will get 0 minus 28. It's negative. Oh, why did I write the full? Just need the negative sign. Plug in 3 here would be 36 minus 28. That's positive. I get rid of the test values. And so yes, acceleration did change at 7 thirds. And so I will say the acceleration is positive, 7 thirds to infinity. And the acceleration is negative from 0, so starting at 0, to 7 thirds. I could also add it, throw in here, and for velocity. The velocity changes at 1 and 11 thirds. And the acceleration changes at 7 thirds. Okay. So I could throw that in as well. It would basically act as like local extrema and concavity. Points of inflection over here. Yes, we have done position, velocity, acceleration before, but this it's a new context, right, with the first and second derivative things we do now. And they're going to answer on that one.